All right, class, welcome back to part dos. All right, so we're just going to do a couple more examples and that'll be it. All right, here we go. So example 2, this time we're given the perimeters. Now remember what I just told you guys is that perimeter is a linear measurement. You can measure the perimeter of a polygon by using a tape measure. So because that is a linear measurement, that goes into my table as a similarity ratio. It's not areas, it's not volumes, it's linear measurements. And as we wrote on our little table earlier, linear measurements goes into our similarity ratio, and that's a perimeter. So here we go. I know that the perimeters are 32 inches and 40 inches. So that gives me a ratio of 32 to 40. But we always simplify it first. So step 1, what ratio is given? This is going to be my similarity ratio because it's linear measurements. Step 2, simplify them and put them into the table. So when I simplify 32 to 40, they're both divisible by 8, I get 4 to 5. So here's my table. I've got my similarity ratio. I've got ratio of areas, and I got ratio of volume. Just going to abbreviate that. I hope that's okay with you guys. Alright, now remember, if this is A to B, this is A squared to B squared, this is A cubed to B cubed. And my similarity ratio is 4 to 5. I'm going to put that into my table right here because it was linear measurements. And then once I have that into my table, I can find the other ratios. The ratio of areas, I'll square those numbers. Will be 16 to 25. And the ratio of volumes, I'll cube those numbers. And 4 cubed is 64. And let's see, what's that? 5 cubed is 125. So ratio of volumes is 64 to 125. Now here's what that means. All right. If I just told you, hey, I have two similar polygons, here's their similarity ratios. All right. Well, if one of them had an area of 16 square inches, the other one has to have an area of 25 square inches, and so forth and so on. Same with volume. So the similarity ratio is 4 to 5. What is the ratio of their areas? 16 to 25. And now finally we're going to work on the last step of this process. Use the needed ratio to set up a proportion and solve. Here's what I mean. If the larger polygon has an area of 200 square inches, what is the area of the smaller polygon? Well, here's what I know. I know the ratio of the areas is 16 to 25. And I know the area of the larger polygon, so obviously that's going to go on the bottom associated with the 25, that's the bigger number, is 200. What is the area of the smaller polygon? So I'm going to use the ratio of areas. I'm going to plug in the area that I know the bigger area. I'm going to solve for the smaller area by simply cross multiplying and solving this proportion. All right, so when I cross multiply, 200 times 16 gives me 3,200. So 200 times 16 is 3,200 equals 25x. Then I'll divide both sides by 25, and I get that x is 128. I just found the area of the smaller polygon, so I'll write my answer is 128 square inches. The idea here is that I don't need to know the dimensions of the polygon. Typically, if I wanted you to find the area of a polygon, you would even need to know, is it a rectangle? Is it a triangle? Is it a pentagon? What is it? We don't know. And we don't know the dimensions. But we do have enough information because you know one of the areas and you know they're similar, so you can figure out the other one. All right, let's do another example. All right, my old apartment complex has a pool that is 10 feet deep and a smaller but similar baby pool that is only 2 feet deep. All right, so this is actually a true story. It's not actually an apartment complex, but when I was a kid growing up, we had a neighborhood pool, and the pool looked like this. Let's see if I can accurately draw this pool here. It was L-shaped. This part down here was like the shallow end, and then there was a deep end over here. And then this stuff in the middle here was just like kind of middle. I don't know. All right. Then there was a little baby pool. The baby pool looked like this. It looked the same, except for it was just like a little smaller version. So how creative. They wanted to make them similar to one another but the baby pool was smaller. Now, one thing is that I'm telling you that this entire pool had a universal depth of 10 feet. That's not really true. The depth in the big pool used to vary in that swimming pool, but the baby pool's depth was constant. But in order for us to do this problem, they have to be similar in every way, so they both need a constant depth. All right, so here are the two pools. All right, so this pool is 10 feet deep. This pool, which is smaller and similar, as I've drawn, is 2 feet deep. Now, what I've told you about each one of these things is I've given you linear dimensions, depth. I haven't given you area. I haven't given you volume. I've given you linear dimensions, which is depth. So a linear dimension always goes into my table as a similarity ratio. So I know that from the big pool to the small pool, the ratio is 10 to 2 or 5 to 1. So now I'm just going to plug into my table. This is similarity ratio, ratio of areas, ratio of volumes. And remember, in the original table, this is a to b, a squared to b squared, a cubed to b cubed. Well, what do I know? These are linear dimensions, so this is my similarity ratio. What this tells me is that every linear measurement in this pool is 5 times as much as the linear measurements in this pool. That's linear measurements. To get the ratio of areas, I square that. 5 squared is 25, 1 squared is 1. What that means is that any area aspect of this pool is 25 times as much as the area of this one. So for instance, like the area of the bottom of this pool would be 25 times as much as the area of the bottom of this one. And then the ratio of volumes I find by cubing my similarity ratio. Well, 5 cubed, as we know from the last problem, is 125. And 1 cubed is still 1. I know, in terms of volume, there's 125 times as much volume in this pool as there is in this one. All right? So I found the ratio that was given. I simplified it, and I put it into my table. I found out the remaining values of my table. Next thing is determine which one I want to use. So here's what the problem says. The larger pool holds 25,000 gallons of water. How much water does the baby pool hold? Well, gallons and how much water is volume. So this is the ratio I want to use, the ratio of volumes. And I know that the ratio of the volumes, the big pool over the small pool, is 125 to 1. Well, I know the larger pool has a volume of 25,000 gallons. I want to find the volume of the smaller pool. So I'll cross multiply. I get 125x is equal to 25,000. I will divide both sides by 125. And I get that that little tiny baby pool has 200 gallons of water. Now it is a baby pool, so I could go on a little extension on this problem. And I could say, like, suppose the baby pool is 30% urine. How many gallons of pee are in the baby pool? Well, you could just do 200 times 0.30. Oh man, 60 gallons of hot, disgusting urine floating around in that baby pool. All right, that was a joke. I'm not going to make you find out how much pee is in a pool. All right, and then the last example. I wanted to do one that dealt with weight. Okay, I told you in the very beginning, anytime we're dealing with a problem that has weight, we're going to use the volume because they're going to have the same density. All right, so two metal spheres. Now I notice it doesn't say that they're similar to one another, but you guys, spheres, all spheres are similar. Just think about it. Okay, here's one little sphere. Here's another sphere. They look exactly the same, just one's bigger than the other one. Okay, so I know that they're similar to one another. So they weigh 864 pounds and 500 pounds. All right, now remember what I told you in the beginning. Weight is going to go with volume. Because any problem I give you with weight, I'm always going to say it has the same density. So the volume will determine the weight. So I know that the ratio of volumes is given. And that is 864, to 500. All right, let's simplify this. Let's see. Probably divide them both by, I don't know, let's see. Divide them both by 4. Let's see where that gets us. That's 216. And then 500 divided by 4 is 125. Now, I know that those are perfect cubes. You may not remember that, but check it out when I plug this into my similarity ratio. Hang tight. I'm going to pause and show you how to use your calculator. Hang tight. All right, guys. Sorry, I'm back. All right, so we have our table. Similarity ratio, ratio of areas, ratio of volumes. All right, every time you're doing one of these problems, make sure you use this table. I know the ratio of volumes is 216 to 125. Now, I also know that if I know the ratio of volumes, this is A cubed to B cubed. To find the similarity ratio, that's A to B. So that means I need to cube root these numbers. All right, so let me bust out my calculator and show you how we can cube root. All right, a couple options. One, if you have a scientific or graphing calculator, there's a cube root option. It kind of depends on the calculator. But for mine, if I go to the math button, you can see option 4 here is a little 3 in front of my square root symbol. So the index is 3, which means cube root. And the cube root of 216 is 6. And I'll find the cube root of 125, which we should know after the other problems, is 5. But let me just show you in the calculator. It's 5. So the similarity ratio is 6 to 5. And that means the ratio of areas, should I need to know that, is you square that, a squared to b squared, which gives me 36 to 25. Now, if the larger, one other thing. Suppose you can't find that option in your calculator, and I showed you this before. If you can't figure out how to cube root in your calculator, the other option is you can raise to the 1/3 power. Let's check it out. If I do 216 and I raise it to the 1/3 power, you'll talk about this in Algebra 2. That's the same thing as cube rooting. You get 6. 125 raised to the 1/3 power, same thing as cube rooting. I get 5. So it's another option should you need to do that in your calculator. So last step of this process is, well, what do we want? If the larger sphere has a surface area of 72 square inches, what is the surface area of the smaller sphere? So what ratio do I want to use? I want to use ratio of areas because, again, it's telling me the area. So the ratio of areas of the bigger to smaller is 36 to 25. And I know the surface area of the larger sphere is 72. I want to find the surface area of the smaller sphere. So when I cross multiply, I get 36x is equal to 72 times 25, which is 1800. And then I'll divide both sides by 36. And I think we get 50. And we do. So x is 50. And to answer my question, what's the surface area of the smaller sphere? Well, it's 50 square inches. There you go, you guys. So this could be a little complicated, but what I'm telling you is when you're doing these example problems in today's assessment, I want you to follow those 4 steps. What's given? Put it into the table. And that's exactly what we did here. We simplified it, put it into our table. We found the other ratios, and then we used the one we needed to solve the problem. So give it a shot, and if you need any help, just stop by the office hours or during class in the Google Hangout and ask, and I'm happy to help out. And so is Miss Butler if you're in her class. All right, well, you guys have a great day. Again, just let me know if you need anything, and I hope things are going well with home learning. All right, take care.